Okay. Good morning, guys. Again, here Gilberto Lima Thomas from Brazil. Um, and today I'm going to present this module 4.1, external potential on and forces on cells. Okay. This, as Hayden just talked, the workshop is live streaming and recorded and distributed on YouTube. Today's modules we will cover this list of topics, and the motivation for this lecture is the single cell migration, persistent time, how to implement it, persistent time in migration, and the use of the external potential will be given through a series of 5 exercises that will be mostly coded during the presentation. Okay. Okay. The big question is, how do the living cells move? Huh? How they know where they are? They don't. The James told yesterday they don't have eyes. They have to sense their environment. And you do know that the cells crawling in migration is everywhere in the process of building a organism. So in many biological processes, since the beginning of the life, we have examples, for example, for embryonic development. The first gastrulation step in the formation of a organism involves a lots of cell movements, since the formation of the blastula to the gastrulation with the invagination of the ovulum. And another good example of cell migration is wound healing. If you have some injury, the cells on your body comes to that injury, and eventually they will be closed. Um, Inflammatory response to any kind of the disease you have. No, blood cells, white cells come to your uh, inflammation and attack the inflammation. Everything is done very fast. So the crawling of this kind of cells, the movement of this kind of cells, is very powerful to reach the source of the disease. Also, the cancer metastasis is a process where single cell crawling is very active. No? The cells move through the bloodstream, and eventually they get out of the blood vessel and form another blob of cancer cells, and you have the metastasis. So cell crawling has a very good a very big interest for us. Now, how do the cell move? Well, we know that move for different mechanisms. These mechanisms can be external ones, like here we have the sperm cells moving by flagella movements, the tail of the cell. And in this other side here, we have the cilia movement, where the paramecium, for example, moves with these tiny hairs around its body, and this is used to move. It's like swimming. Okay? But the migration, the movement mechanism can be internal. For example, here we have 3 different kinds of movement. The first one is the lobopodial movement. The cells stretch in some strange way, forming these structures in front of the movement, in the direction of the movement, and pull the nucleus up in that direction. The other kind is the amoeboid movement. Uh, Again, a different structure is formed in front of the cell, with a bunch of stress fibers attached to the nucleus. Also, the nucleus is pulled towards the front. The nucleus doesn't have an intrinsic movement, the cell has. And finally, the lamellipodial movement, where there is a formation of a structure in front of the cell, which calls the lamellipodium of the cell, and that moves the cell where she wants to go. Okay? In this study here, in this lecture, we'll focus our attention is the lamellipodium movement. This one. Let's go. The motivation, continue with the motivation. Even if lamellipodium movement, there are kinds of trajectories followed for the cell. See here in this quick movie that was the only one I found. In the first part, we have cells just uh, fluctuating around a certain position. In the second step of the movie, you see this here. See is only fluctuation. The next one, the cells go in one direction, a persistent movement. It's quite fast. In the last one, the cells fluctuates, move, fluctuates, move, fluctuates, move, and so on. See? This is the last one. It oscillates, stops, move, oscillates, and go on. So this last movement is what we call the persistent random walk. Okay, and how the cells the lamellipodium is formed to achieve this kind of movement. The lamellipodium is formed after a bunch of actin fibers. The stress fibers are formed in the front of in the region of the cell with this intricate mesh here of proteins that are put together by a mechanism like that. In the real front of the lamellipodium, there is this actin meshwork, which is in a zoom, we have this kind of formation of fibers. So the monomers of actina, these yellow small circles here, attached to the front of the fibers and push, push the front of the lamellipodium in that direction. What do we mean is that this formation of monomers here exerts a force on the edge of the lamellipodium, moving the cells in that direction. At the same time, at the rear part of the fiber, the monomers are being disconnected from the fiber. And there is a recycle of monomers, the ones which are detached from the rear part goes to the front part, attached, and then you have this kind of cyclic motion of monomers, assembling, put together in the front and detached from the end. In this movie here, you can see the formation. Here are the monomers. The monomers are going to the front of the cell and pushing the lamellipodium downwards. Okay. Now, I should mention that lamellipodium movement is characteristic only of eukaryotic cell, animal cells, for example. And a very important thing, as I mentioned before, characteristic of this movement is the existence of a persistent random walk. What does that mean? Means that if you look over the cell during a long time, the cell movement during a long time, you have a random walk. But if you decrease your window of movement, you have a persistent walk. like that one in the movie. The cell oscillates in some region, like here, then change directions because it stops for a small amount of time. The lamellipodium reorganize in another direction, and the cell moves in that direction. So if you are looking at a small window of time, interval of times, the movement is preferential, is persistence. But if you look at the whole movie, the motion is round the walk. So you have a persistent round the walk, a combination of these two kinds of movement. Okay. Uh, Now let's bring CompuCell 3D to the game. Uh, Cells that we create in CompuCell doesn't doesn't have persistence time, doesn't have persistent movement. They only move randomly. CompuCell is a stochastic is based on a stochastic probability function. Remember the Boltzmann probability? So to get the persistent handle walk, we will have to impose this persistent handle movement by hand. Okay, so we will uh, implement a mechanism that will have this kind of motion, the persistent handle walk, in the cell. How do you do that? Well, we know that the simplest way to implement persistence is forcing the cell to move in a given direction. Okay? How do you do that? Again, a little bit of physics now. We saw that in previous lecture. Uh, Differences in potential energies produce force, and we have our CompuCell 3D based in energies, in difference of energies. Okay, so if we introduce in our effective energy a term that will force the cell in a given direction, like this one, see, this is a scalar product of a force in a given direction applied in a certain position and making the cell move in the direction determined by delta x. Okay, again, F is the applied force. XY is the point where the force is applied. And the delta x is the resultant displacement of the cell. So if we include a term like that in the Hamilton, in the energy of our system, we will have a force acting over the cell. Okay? So this is the function of the external potential plugin that we will be talking today. Okay? You can find the external potential in the manual. You go to let me put over here just to show you where you can find more for external potential. Go to the CC3 manuals page here. Go to the reference manual, type external here, and you'll find the external potential plugin here. You can find very easily and well explain how to use it. I will try to do that today. So let's go. So the external potential then is the product of a strength, which is actually the force, times scalarly multiplied by the displacement of the cell. So the displacement of the cell is well known because you know where the cell was and where the cell is in your simulation. Okay, this is a external parameter that you impose over your simulation, the intensity of the external potential, I mean the force. So since we have here a displacement and the displacement is a vector, no, you have to know the 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 components of the force that act in this scalar product. I mean, opening this expression here, we have this kind of expression. So the external potential is has three terms, one term in each direction of your cell movement, delta x, delta y, and delta z if you are dealing with your 3D simulation. And you have to know the components of the lambda vector in each direction. Okay, so these pictures may be more clear. Huh? Here is your cell. This is the applied force on your cell, and the cell is moving in that direction, for example. Okay. Um, See, there is a negative sign here. So as the force is minus the derivative of the potential, if you want to the cell move towards a positive x, you must apply a negative energy, and vice versa. Because remember, force, where is that? It has this kind of sign here. Let's go. Let's implement that. But now a little words about periodic boundary conditions. We have been dealing with periodic boundary conditions. Pedro yesterday talked a lot about boundary condition, periodic boundary conditions, but I think we have to understand what's that. What does that mean? Okay, in this, let me say, a periodic boundary condition says that, for example, here is your xy plane. This is a coordinate in this in your xy plane. Suppose now you have a cell moving. I will do a small drawing here. Not very clear, but here is your grid, your xy plane. Your cell is moving here and going in this direction. It will supposedly the cell will stop at this position. But it seems that this position is outside of the grid if you don't have periodic boundary conditions. If you have, the system understands that you have to copy your whole XY plane here. Exactly. Ah, a second. Okay, here. So the cell is moving here. Okay? So it's like this border, the right border of your um, plane is connected with the right one. Understand? So the cell will appear at this position here. It's as a continuous plane. The same occurs at that direction. If the cell is moving upwards towards that direction, then you have another grid being copied here. And in fact, your cell will appear here. will come, will enter in your system from downwards. Okay, this is what periodic boundary conditions means. So you have the connection between right and left borders, and the connection between up and down borders of your grid. So in this small movie here, you can understand better how does the grid real looks like. See, here's your plane. You are now it's connecting the up and down parts and the right and the left one. So you have actually a torus shape. And if you put something to walk over the surface of this torus, it's like an infinite grid. There is no end. So this is a trick you use to make his simulations look big, huh? Because now you have an infinite space for your cell walk. It will never find, the cell will never find the end of the space. It will never stop. Okay? So that's contents. Now the first exercise. I will have to now to bring the to edit here. The exercise will be this one. Let's build a simulation where we have a single cell in a grid 256 by 256, and the cell is forced by an external potential which has these parameters. Lambda vec x and y equals to minus 20. It's quite easy. Everyone knows how to start a new project now. Let's try to do this quick. E1, next. 200 fixes, 1. It's a 2D simulation so far. But we have now to include the periodic boundary conditions. So both in the x and y directions. Square, rectangular, no, let's put a block. Move, moving cell. Next, no chemical, contact, volume, and now you have here external potential local flex. Remember the difference between those two kinds of plugins. If you choose the first one, volume flex, surface flex, and external flex, the values are defined for all the cells in the XML file. If you choose the local flex, the values will be defined on the Python steppable file. Okay? And center of mass. Next, finish. Now we have to create the cell at the center of the grid. Radius, let's put, how big is the cell? Let's put 10 here. 10 here. And let me see the external potential uh, here. So here is the steps. We have everything. Oh, I choose another one. And I know it's the same, right? And here in this in the screen, I forgot I put a uniform initializer, not a blob initializer. So here I have a square of size 10, and here I have a circle of radius 10. Okay? It's not much difference. And then we have to in the start function of your steppable, give the size for the things. See? Again, uh, I will copy this for here. I will give it to cell font target volume equals to 300, like the exercise tells you. Cell dot equals to 10. Okay? Save. And let's see if it's going to work. Again, remember, you can find this exercise ready to go on the student materials under the name 4111 zip file. Okay? So, oh, why it appears 3 cells? Ah, I see. Here, I should have only one cell here. It's funny. Something is. I have 5. I should. I'm going to change just a second. Let's see. I can replace this steppable by the uniform initializer here. Get rid of this one. Down, move. Now I have the correct one. Ah, of course. Here I have to define the size of the cell. Since I want to a cell with size 10, I have to define a region, box mix and box max, of 10 pixels of size. See? 2029 with 10. Okay, there we go. So if you put this to run, doesn't happen anything. The cell just fluctuates by the how did I get the oh, it's so fast the chat I cannot
I am handling it. Don't
okay,
worry,
thank you,
Gilberto.
Pedro. So the cell isn't there is no force acting over the cell, so the cell is still there. moving just by fluctuation of the temperature, that word. Okay, now we have to impose the motion. How will you do that? We have to add those lines here to the step above in the start function again. So the lines are, I'm saying that the cell lambda vec x equals to minus 20, and the same cell dot lambda vec y equals to minus 20. What I'm saying here, I'm saying that here, I will go back a little bit, that this component of the external potential, the fx component is minus 20, and the fy component is also minus 20. Okay? Let's go there again. So now you can start again the and then your cell is moved. And this is a good example of periodic boundary condition. See, the corner of the grid is shared by the other three corners. You can see the cell appear in other three corners at the same time. Another thing is that since I gave equal values for both lambda x and lambda y, the cell moves on the diagonal of the grid. I can, let's see if I don't know. Here I cannot change the value. If I come here, for example, and put lambda 50, for example, okay, it's not in the diagonal anymore. So this motion is completely persistent because the cell doesn't change the direction during the movement. Okay, let's go and continue. Now we, okay, I go over this already. So let's make now the cell accelerate. To do that, we have to change the value of the force during the simulation. Okay? We do that for doing the following. See, we stabilize the initial value for the lambda vec, x and y, but now we are going to change it in a certain interval of time. So I will define here my time interval. Say 100 Monte Carlo steps. But I'm saying that each 100 Monte Carlo steps, the cell direction, the force will change, but we will keep in the same direction, okay, for now. Let's go back to 20 here. So I have to add lines onto copy here in the step function. I will start with a condition with the condition to change the cell direction. I will ask if Monte Carlo step divided by time interval. It's equals to 0. Oops. 0. Then what? I don't need to do that, but because I have only one cell. Anyway, in self, oh, self, uh, in cell list, then I will accelerate. It's minus float of MCS divided by time interval, or by 1/2. The same to the other. Okay, so the acceleration is if Monte Carlos is 100, it will be -1, -2, -3, and so forth. Okay, go to why is not even something happened. Is that an error? Ah, I made a mistake in misspelling in here. List. See, the motion starts slowly and then increase according with the Monte Carlo step. See? Okay. Let's see what is going on with the speed of the cell. So we create that's what I have said. And the step function, I include that part. And now we saw what happens. Let's go on. Now we have to calculate the speed of the cell. Another part, we have to put some physics in it. Let's do it. How do you calculate speed? Well, speed is the ratio between the displacement and the time interval of time you have that displacement. Since velocity is a vector, you have to calculate the speed in all the directions of your movement. How do you calculate that? Using these fractions. We know the position of the cell at the time t and in time t plus delta t. But we have to keep track of these positions. Oh? And the position of the cell is now you are going to see how it works, the center of mass plugin, which has always been loaded with any simulation so far. Okay, the center of mass plugin keeps track all the time of the center of mass of the cell. Okay, it's a point in the grid which has three components, x, y, and z if you are in 3 dimensions. So to calculate v in the x direction, y direction, and the speed, which is the sum of the square of its components, the square root of the sum of the square components, we need to calculate also the center of mass, and applied force is also, because remember here we have the components of the force, vec x and vec y. The intensity of this force is the strength of the force is given by the square root of lambda vec x squared plus lambda vec y squared. Now we have to implement this. How do you do that? Again, I will continue in the same simulation, okay? Again, you can find the simulation in exercise 4113.zip in the student's material. So here it goes. We have these components here, and here I will create a dictionary entry for the cell where I will keep track of the center of the mass position at this time. I will call O, do you understand later? Old XCM equals to 0. Cell.dict old YCM, oops, CM equals to 0. And to see the speed, I will add a graphic window. Python plots here. The next exercise, I will grab it, the one I have ready, and I will go over it to not, because typing is going to be much more often here. So I will call cell speed in the title. And here I will put force strength, lambda vec. This bars means modulus of lambda vec. And here is modulo of v, which is the speed. Okay? So I will get rid of this line here, only one, and the placeholder for the graph is split. So we adjusted the start function. Now we have to adjust the step function. Now it's tricky because there is a lot of typing here. I think I'm gonna load later. This part, let's understand this yellow window here, okay? I have to calculate Vx, I have to calculate the displacement in that interval of time. Okay?
Gilberto,
Yes?
maybe that's a good time to wait for people to catch up because some people are still
Oh,
coding the
okay.
plots. So I will launch the poll here to see how
Okay.
they're doing with it,
Thank
and
you,
then
Pedro.
okay. Yeah, I'll have a lot of people trying to catch up now, so
Yes, I will wait a little bit. While, while I wait, I will load the
Kimberly, I'll join Kimberly in the breakout room for a second.
somebody needs to help Yasmina. Her cell isn't moving. Okay. Yuxa, at the start function, you, yeah,
Yes, remember we said the cell
yes,
dictionary old XEM equals to 0, right?
yes, you're right, you're right. I mistaped that. It's X at the start function should be cell XCon and cell YCon.
Okay, okay.
I will correct that. Okay, I will continue. Okay, slowly. Uh, Correcting what Hixa just noticed here at the start function. The dictionary starts with the actual position of the cell, the center of mass of the cell. This is why we refer to the center of the mass of the cell. X dot cell dot XCOM, center of mass, and C dot YCOM. This is the general use for the center of mass plugin. Okay, so at this Monte Carlo 0 step, the cell is in this position, not 0. Okay, now continue with the explanation about the code. So dx is the difference because now we are in the Monte Carlo's step 100, for example, because the only way to enter in this window here is if this condition is satisfied. So MCS must be 100 here. So at this time, the cell center of mass is cell.xcon and cell.ycon. So the delta x, the displacement, is the difference between the actual position, cell xcon, minus the old position which was stored in the dictionary. So I have this delta x written here. Now, we have to take into account the fact that our boundaries are periodic. So, again, let's come with that picture here. If the cells go from here to here, I have to see if this cell actually is in this position here. Otherwise, we will have see, if the cell moved from here to here, actually the cell moves from here to here. And this X and Y center of mass are smaller than this X and Y center of mass. We have then to correct the displacement for the size of the grid. So if it is displacement, the size of the displacement, the absolute value of the displacement, is bigger than half of the grid, so I have to reposition the displacement to the right position. So the x must be decreased for the absolute value of the displacement. The same thing has to be done with the y position, because the cell, if the cell is moving in that vertically, no, this position here actually is this position here. So if the cell moves, see delta y is bigger than this half of the size of the grid, so I have to correct. Understood?
I have a
Okay.
question.
Hmm.
I'm sorry to interrupt. I have a question. So why is it exactly half? So are you initializing the cell to be right at the center at time t equals 0?
I think I didn't get. Why do I doing that?
So you are updating in line in that
Yes. Axia called me the attention about that. I have to here. The initial center position is the position of the cell in Monte Carlo step 0. Cell xon, cell ycon.
Oh, okay. So you are initializing the cell to be right at the middle of the block.
Yes. Because we did that here, remember?
Okay, got that. I'm sorry, I missed that. Sorry.
Okay. So the next part of the code, I am calculating the speed and the lambda vector. See, here, the speed is calculated at the square root of dx squared plus dy squared over the time interval, which is, remember, here, this expression here. Huh? And in the next line, I am calculating this lambda vac strength, which is, oops, line line 43. Okay, once you have this calculated, we can plot it. Okay, the final code, which is the one you have in the student's material, is this one. Okay. Then I include the plot window. And finally, I update the dictionary entry for the old position of the cell as with the actual position of the cell. Good to go? Let's see. Yes, that's true. You have here the simulation running. I will decrease to have the slide. The cell keeps. See, here I am plotting V against force, speed against force. The force increases and the speed increases. But something is going on here. The speed is attaining a constant value, even with the force increasing. Okay? So this is what we're going to have at the end after a long time of simulation. The cells goes to a constant value, no matter what force is being applied to the cell. And why does that happen? Why does the cell reach a maximum value of its speed? No, it's really slowly. Maybe, Uxia, if you try to decrease the size of the grid to 128 square, then you have a more fast simulation.
But where should I modify it in the XML file?
Yes, yes. Don't forget to update also the uniform initializer divided by 2, the position of the initial cell.
Okay. Thank you.
Yeah, something like that. Because if the cell is finite, you have a size for the cell, and the force is being applied to the cell, to each pixel of the cell, and since you don't have more, how do you say, the word is missing. I mean, since you have a finite size of the cell and you have a grid, you cannot impose more force than the cell can handle. Okay? The maximum displacement for the cell during that Monte Carlo step is determined by the size of the cell and from the probability function. You cannot move the cell more than 1 pixel per Monte Carlo step. one pixel per time interval.
Could you explain that again?
What?
Could you explain that part again, why the cell speed is getting constant?
Just see, you have during one Monte Carlo step, the cell can, if all the pixels can move, the amount of pixels that can move is the size of the cell. Okay, so when your strength when your force increase, you remember the probability function delta H over T. If your strength are increasing, delta H is increasing. So your probability of change flips is increasing, but the maximum number of accepted flicks is the size of the cell. Então, if the force can move, can be the force can be high enough to all the peaks of the cells being accepted as flips, the maximum number of the accept flips is the size of the cell. So even if you have more force acting over the cells, you can increase the probability of function of acceptance flips during the one Monte Carlo steps. Understood or not?
So a question built up on that. If we, instead of increasing the size of the cell, we maybe allow more Monte Carlo steps to happen or do some kind of like change the time scale of things, change the time scale of the
Yes,
force versus
probably. You can try that later today. Change the for example, keep this force as is and change the initial size of the cell, the
perfect.
target of the cell, to see what happens with the graph.
Okay.
Okay?
So is it
Thank
true
you.
that so is it true that even if we increase the size of the cell and continue with the simulation with the same force, so is it true that we will still reach a kind of like asymptotic velocity, but the slope will be much less than
Sorry,
what
I'm not understanding. The sound is not very good here.
I'm sorry.
Can you type it maybe?
Okay, I'll tell.
Thank you. So let me go ahead and to the next step. Let's go now to next exercise here. Now let's try to build a more realistic cell. These cells like that. The lamellipodium movement. See, the cell spreads some part of his body, creating the lamellipodium part, moves in that direction, maybe stops. See, it's not very clear here, but see, here is the lamellipodium. It's a very thin part of the cell. Okay? And there is a very interesting model built by Abercrombie, where it says that the cell has 4 basic constituents. This is how the cell crawls. We have the nucleus, the cell body here, the cytoplasm, the lamellipodium, and the substratum where the cell is attached to. So what happens? There is a tension in the cell cortex that here at the tip of the cell, it's protrudes with the formation of that is fibers from actin monomers. this protrusion attached to the substrate, stick to the substrate, formating focal points, focal contacts, integrins mediated contacts. And after it sticks the front part, it releases the real part and contracts it, and the cells move to the right, and things continues. So this is the cycle. Protrudes, sticks, release the rear, and advance. Okay? This is a mechanism proposed by Abercrombie. So let's try to do this, a cell like that. We'll have to create now, since we have these three parts of the cell here, nucleus, cytoplasm, and lamellipodium, and where the cell is attached to substrate. Okay, this is going to be our simulation cell types here. So let's go. At the beginning, we'll create this only the three-part cells. I will close this project here. And now I'm going to open the 4, 1, 2, 1. This one. I'm not typing anymore. I will get it ready to see. Okay, so in the XML, I created three kinds of cells that I called cyto, lamel, and nucleus for the three components of the cell. What I'm doing is I will create a cell which is built of three parts, three different cells, cyto, lamel, and nucleus. Okay? I will later apply a external potential, but at the beginning we have this situation here. When I create only this, I will show the picture here. I have to define now the size of the cell parts. Let's say that the volume of the cytoplasm is 300. So I would say that the volume of the lamellipodium part is 1/3 of the size of the volume, and the volume of the nucleus is 20% of the cyto volume. So I will have 390 and 60 pixels for nucleus, lamel, and cytoplasm. Okay? This is very, very easy. If I put the initial simulation you have just created to run, at the beginning, we will have this, let's see here, open and play. There is the player here. It never goes.
Gilberto, we have a question in the chat. What's the current code they should open to follow along?
What?
What's the current checkpoint code they should open to follow along? 4.
Oh, yes,
Four-
it's
412
better
what?
to open. I told you that to avoid so much coding right now, because we want to have that time. Let's grab the simulations that are ready in the student's material. Now
So
the first one is 4-1-2-1, after 1-2-2-1-2-3.
Got it. I will put a link in the chat for everybody.
So this is what we see at the beginning. Just the 3 cells with the different colors, seed, cyto, lamella, and nucleus. Purple, green, and yellow. If you put that to run at the beginning, if you don't adjust any energy, contact energies, the cells will not achieve what we want. I mean, what the real cell doesn't look like. We have the cytoplasm, the nucleus inside the cytoplasm, and the lamellipodia involving the cytoplasm. Okay, outside of the cytoplasm. Okay, so at the beginning you don't have that. We will have this kind of situation if you don't adjust the energies, the contact energies. I mean, we have to impose that hierarchy in the contact energies that will put things in the right position, as James told it in, I think, in the first or second lecture. Okay, so we have to change the energy values in the XML file. It's correct already. See, the green part of the code is commented, is the values loaded by default. To find these correct values to have the correct shape for the cell, the structure for the shape and the structure for the cell, it's a kind of tedious because you have to play with those energy values, and they are a lot. 10 actually. 10 values of energy to play. I did that already, so I can, if you want to have it, if there is someone coding here, I can copy and put in the chat, okay? Once you have this fixed, we can run the simulation, and you can see that the cell will have the right shape we want. A structure, actually. It's a nucleus inside the cytoplasm, surrounded by lamella. Okay? But still, the cell isn't moving because there is no force applied to it.
Gilberto,
Okay.
while this runs, we have a good question in the chat. How did you obtain the parameter values? How do you know what values to put in?
By force, trying, changing and looking, change and looking, change and running. Of course, you can use these values you can change the values here in the contact windows. For example, you change something here from 40 to 5. You see what happens. See? The nucleus get outside of the cytoplasm. But I can, so playing with those values here, of course you have a guess from the beginning, which value you should have. For example, if you want to nucleus be inside the lamellipodium, the cytoplasm, and then the energy between them should be smaller, because nucleus like to cytoplasm. And otherwise, nucleus doesn't like the lamellipodium. So the energy between nucleus, let's see here where it is. Nucleus and cytoplasm is 10, is higher. So nucleus doesn't like to be with cytoplasm, with, lamel. Where is lamel? Here. Lamel and nucleus 40. Nucleus hates lamel. Nucleus and cyto 10. Nucleus prefers to be inside lamel. Okay, and with medium, where's with medium? 100. Medium hates the guts to be near the medium. 100. So it never will touch the medium. So knowing this relationship between the cell types, we can have a guess at least to start to find those values. Okay, it's a work. So now we have to impose the movement. So everything is written here. The question is, use the external potential plugin to make the cell move with a random orientation. So we are now creating that persistent random walk. The cell will move in some direction, then they will change the direction of the force and move in another new direction. Okay? How do you do that? Again, I will load the right code here. Do you guys do the same? Now it's the 122, I think, open. Simulation, I have it here. Let's stop this one. And here, how you do that? So let's analyze the code now. First, again, I will create a time interval variable here, parameter. Put it as 1,000 Monte Carlo steps. This is our interval. And I will load from the Python library a function called uniform. This function gives you a uniform distribution between some interval of data you want. Okay, let's do that. Então, there, here. And the step function is the place where you have to change the orientation of the force. So you say that if Monte Carlo step divided by time interval is 0, is the trigger event for the direction changing. I will change the lambda vec x and vec y to this value here. 120 times a random number from the uniform distribution between minus 27 to 0.27. This is absolutely random number. You can choose something, what do you want? Remember, uniform distribution, I think the default is between -1 and +1. So I stretch this interval to have it more, the changing more often, to not spread too much. The question, cell lambda vec should be cell lambda, line 37. Oh, yes. Thank you, Vixen. This capital letters keeps me crazy. I will fix in the students' material later. Please, thank you. So, and I will update it. Look, I am updating the lambda vec x and y just only if the cell is a lamel type. I mean, the force will act only on the lamel part of our composed complex cell. The force doesn't act in the nucleus or in the cytoplasm. That means that lamel will pull the cell every time. Okay? Let's see. Now I think I can run. And you have just again, when you mess here with the player in the Zoom window, I have to start up. Look, now the cell is changing its direction, and the cell is pulled by the lamellipodium because the force is acting only on the lamellipodium. It's good, isn't it? Now our cell is becoming similar to a real cell. Of course, the lamellipodium is always in the same place. I should maybe another improvement on the cell would be disappear with the lamellipodium and appear it in another place, like the real cells do. Okay, going further. So you have seen now the simulation. Now we want to see the trajectory of the nucleus. Okay, the trajectory of the nucleus can be seen by plotting its center of mass coordinates in a graphical window, which is in the 4, 1, 2, 3. So again, we'll go to the start function. We add that graphical window. We create the graphical window. And here, after you change the direction of the lambda back, you plot in that window the for the nucleus type of the cell, the X cone and the Y cone in the axis of the graphical window. Let's see how it goes. Here's the trajectory. Persistent part is the straight lines are the persistent part. The vertex of the trajectory are the random part. You guys got this exercise? Were you able to run it? Okay.
So Gilberto, we are coming up here on 11:30.
Okay, I will finish with one more exercise. Do I have time? 50
Not
minutes? Not really. Well,
No, we
somebody.
can't move back today. What was left?
Okay, let me finish with only one example here. I will just use it to run.
Yeah, just
Put
show it
to run.
running. So for the next 5 minutes or so, everybody just watch what Gilberto is doing. Don't try to follow along so we can get to the next session, but we do want you to
Okay.
see this final example.
Yes. Okay. Let's go ahead here. And I will introduce you. I will this is what you see. The last part of this talk, I would talk about the 3D complex cells. Okay, how to make a 3D cells to move, how to create the 3D cells, and how to make it to move. Okay, so this is in the example I load here. Projects open 4133. I will get the last one to have it done. Close here. So in this example, you can follow in the exercise, the zip files. We are going to create a 3D cell. Again, you have to adjust the energy, the contact energies to have that realistic structure. Nucleus inside the cytoplasm surrounded by lamellipodium, and make it to move with the external force. Okay, I will go through the final part. This is, and I will show you the simulation here, this part. So this is the code. Now we have 3 parts. We continue to have 3 parts, but now we are including an extra component in the simulation, which is the substrate. The substrate is something where the cell is attached to, and for example, you can play with the substrate to see how the cell moves on different substrates, for example. And this kind of component is frozen because it doesn't flips over the cell, if you want. Again, we have the substrate, the external potential, the adjusted energies. Now we have the extra type here. We have to adjust again the contact energies between the 3 kinds and the substrate, and so on. The creation of the initial state is that we create 3 cubes, cyto, lamel, and nucleus, and the substrate is a layer. It's the bottom layer of your 3D grid. Okay, Z equals the XY plane, the total XY plane, and Z equals to 1, only 1. Okay. In the steppable, basically the same as before, just now we have 3 components. And in this example here, because you know the lamellipodium have a very thin attachment to the cytoplasm, because the lamellipodium is a very thin structure of the cell. So here, to have the whole cell movement, I forced the force to be acting over the cytoplasm too. Okay, so just to run it. One thing you should do here is, when you have 3D simulations, you might, let's stop here, pause here, to get rid of this cell border visualization, because this feature activated will tell to the CompuCell to rendering images. So this is why you are seeing here in the substrate is small squares here, or small cubes if you want. So because it's trying to draw the surface of each component of the substrate. So you get rid of this, and your simulation will be much more fast. Okay, so let's play. See, this is our 3D cell moving at the same way as before. It's a bit more complicated to adjust the parameters, as I said, because the lamellipodium is too thin. It has a little contact between it. See, this is the problem that you have when your energies are not so well adjusted. The lamellipodium escapes from the cell. Finally, Hayden, let me just show the movie. I have a new project here, which is the cells flowing in a tube. Where is that? I lost the player. Where's the player? Now let's start over. Now I want to see the cell borders because this is a 2D simulation. Okay, I will activate the cell borders visualization. See, and there you have. See, this is a very cute simulation where you have here cells being created in the left side of the tube. There is some force acting over them, and this force is pushing towards this the channel. And after the channel, they found an obstacle. After they pass the obstacle, the cells disappear. It's like there was a sink here, and the cells disappear. You can see that right away. See, the cells are disappearing the left side, the right side. So this is a toy model that you can do with this external potential to push the cells. The big trouble here, the big work here is to draw this channel step by step. But you can find it in the student's material in this code called E414. Everything is coded here, how the cells move. And here I have cells cells are being created here. In this simulation, in the code, I tell you how to create a new cell on the fly during the simulation. To create a new cell, you have to have empty space in the simulation because you cannot create a cell where does it exist a previous cell. This cell will crash. This is why we have this small line layer of medium at the left boundary here to be able to create new cells here. Okay, so let me finish this. Go back here. This is what is there. Everything is here with. Okay. Thank you very much. Sorry to not having so much time today.
Great. That's no problem. Thank you, Gilberto. So we will go ahead and put all right, looks like the poll has been launched. So if you could please respond to the poll. We'll have a little bit of time here for Q&A through the break if you'd like, but we're going to go ahead and take a break until 11:50, and then Pedro will get started at 11:50 on Module 2. So if you'd like to take a break for the next 10 minutes, go ahead and do that. If you have questions for Gilberto, you can go ahead and ask them now. And again, please do fill out the poll before you go to break. We do appreciate the feedback
Okay, I will stop sharing my screen.